Hi, I'm Chris Muchler, Principal Enterprise Architect and VCDX 257 from virtualelephant.com. And in this module of my Networking Fundamentals online training course, we're going to talk about BGP routing and what the Border Gateway Protocol means for the Internet today. Let's get started. BGP4, as defined in RFC 4271, represents the current iteration of the Border Gateway Protocol, and it serves as the foundation for interdomain routing on the Internet. Its advancements over earlier versions have contributed to the stability, scalability, and versatility of the protocol, making it essential for the functioning of global networks. RFC 4271, which was published in January 2006, defines the current specification for BGP version 4, and it provides a detailed description of the protocol, including its message formats, behavior, attributes, and operational considerations. The latest version of BGP has introduced several enhancements and improvements over its predecessors that we should be aware of. The first is expanded address families. BGP4 now supports multiple address families, including IPv4, IPv6, multicast, and VPN address families, making it more versatile. The second enhancement is increased path attribute support. So we've expanded the number of supported path attributes, allowing for more flexible route selection and policy implementation. The third enhancement is an enhanced route aggregation to allow improvements in the route aggregation and summarization capabilities, aiding in the scalability of routing tables. And we're going to talk more about route aggregation later on in the module. Next, we have improved error handling. So this latest version of BGP, version 4, has defined clearer error handling mechanisms, and this has enhanced the reliability and robustness of the protocol. The final major enhancement is support for CIDR, or classless interdomain routing. This allows BGP to be more efficient in its utilization of IP address space and better route aggregation. As with all networking protocols, interoperability is critical, and so BGP version 4 has been designed to maintain backwards compatibility with earlier versions of the protocol, thus ensuring interoperability between routers running different BGP versions during protocol migrations or upgrades. And it supports mechanisms for negotiating capabilities between BGP peers, allowing them to establish sessions and exchange routing information frequently and efficiently. The most critical thing to remember about BGP is that it has become the de facto standard for interdomain routing on the Internet. It is widely implemented by network equipment vendors and deployed by network operators worldwide. The specification defined in RFC 4271 serves as the authoritative reference for BGP version 4 implementation and deployment. And finally, while BGP 4 addressed many limitations of earlier versions, ongoing developments continue to enhance the protocol's capabilities. Standardization bodies and industry forums work on extensions and improvements to BGP, addressing emerging requirements such as enhanced security, scalability, and support for new technologies. Next, we're going to talk about autonomous systems, or ASs. Now, an AS is a collection of IP networks and routers under the control of a single administrative entity, such as an internet service provider, a large enterprise, or an academic institution. ASs are assigned unique identifiers called Autonomous System Numbers, or ASNs, by regional internet registries such as ARIN, RIPI NCC, and APNIC. And we're going to talk more about these ASNs in a few moments. In BGP, ASs serve as routing domains that exchange routing information with other ASs to enable interdomain routing on the Internet. And so BGP routers within an AS communicate with other routers in neighboring ASs to exchange routing updates and determine the best paths to reach destination networks. There are two primary types of autonomous systems in BGP: transit and stub. A transit AS provides connectivity between other ASs and allows traffic to transit through it to reach other destinations in other ASs. And transit ASs typically have multiple connections to multiple other ASs. A stub AS primarily relies on transit ASs for outbound connectivity to reach destinations outside of the AS. And stub ASs usually have a single or limited number of connections to other transit ASs. BGP routers establish peering relationships or BGP sessions with routers in neighboring ASs to exchange routing information. And peering can be established using physical connections between routers in different ASs or via internal connections, IBGP, between routers within the same AS. We also have AS paths. Now, this is a fundamental attribute in BGP that represents the sequence of ASs through which a route advertisement has been traversed. And BGP routers use the AS path information to prevent routing loops and determine the best path to a destination network based on policies such as AS path length. ASs also have what's called inter-AS routing policies, and we use these routing policies to control the flow of traffic entering and exiting their network, influencing BGP route selection and advertisement. Common inter-AS routing policies include route filtering, route manipulation, traffic engineering, and route aggregation. Another critical feature of autonomous systems is multi-homing. And multi-homing is the practice of connecting an AS to multiple upstream providers for redundancy and load balancing. BGP provides mechanisms for multi-homed ASs to influence inbound and outbound traffic flow, such as BGP route selection attributes such as local preference and AS path prepending. When it comes to autonomous systems, there are also security considerations we must make. And so ASs implement security measures to prevent against BGP-related threats, such as route hijacking, route leaks, and BGP session hijacking. Techniques such as BGP route filtering, prefix validation, BGP-sec, and network ingress filtering help mitigate these threats. As I mentioned a few minutes ago, autonomous systems have what are called autonomous system numbers, and there's two different variants of these ASNs today. The first, which are 2-byte ASNs, were the originals, and this allowed for 65,536 ASNs to be created. Within that collection of ASNs, there are certain ASNs which are dedicated to private ASNs, which can be reused within an organization's network and can be duplicated across organizations without influencing one another, as well as public-facing ASNs. And so you can see here on the slide the ASN number for VMware, and this is the public ASN, which has been assigned to it by the governing body. Now, we quickly realized, much like we did with IPv4, that 65,536 ASNs wasn't going to be enough in modern networking. And that's where we came up with the 4-byte ASN. And you can see with the 4-byte ASN that there are roughly 4.3 million ASN numbers. And this includes the original 65,000 ASNs as well. So now, much like IPv6 for networks, this 4-byte ASN is allowing us to scale autonomous systems in the internet age that we find ourselves today in 2024. As you're starting to realize, there's an enormous amount of information when it comes to BGP, and that's why there's an entire module in this networking fundamentals course dedicated to it. So let's dive into BGP characteristics now so that you can get a broader understanding of everything that makes up Border Gateway Protocol, or BGP, today. So some of the most critical characteristics that we should be aware of is the inter-AS routing. So exterior routing protocols are specifically designed for routing between different autonomous systems, which we just talked about in the previous slide. And so again, an autonomous system is going to represent a collection of IP networks and routers under the control of a single organization or entity with a common routing policy. And those ASN numbers, so those autonomous system numbers, each one on the internet is assigned a unique ASN to be able to identify it within the global routing system. So when I worked for NTT, we had our own ASN numbers. VMware has its own, and like Meta, Google, everyone else who participates in BGP on the internet is going to have their own ASs. And so really when it comes down to BGP, the most important thing to remember is that it's an exterior routing protocol. So in our L3 routing module, we talked about some of the interior routing protocols that might be leveraged, like OSPF. And so it's a path vector protocol, meaning that it's going to exchange information and make routing decisions based on policy and attributes. It's also policy driven. So exterior routing protocols like BGP are highly policy driven. So that allows AS operators to define routing policies to control how routes are accepted, announced, and propagated to neighboring ASs. And policies are based on factors such as AS path, route origin, and local preference. So I mentioned a moment ago that BGP is a path vector protocol. So what exactly is that? So really, it's an approach to keep track of the AS path as a route traverses across the networks. And then this path information helps prevent routing loops and influences routing decisions. BGP is also the internet backbone. So large ISPs and Tier 1 providers operate core ASs that form the backbone of the internet itself. And these ASs play a critical role in routing traffic between smaller ASs and ensuring global connectivity across the world. Another major characteristic of BGP is route aggregation itself. So exterior routing protocols all support route aggregation. Route aggregation involves summarizing multiple IP prefixes into a single route announcement. And this helps reduce the size of the global routing table and conserve resources on the physical networking devices themselves. The internet's routing infrastructure is hierarchical, so it has ASs organized into a hierarchical structure. So smaller ASs are connected to larger ones, and routes are aggregated and summarized as they move up towards the hierarchy, towards the core of the internet. Smaller ASs are connected to larger ones, and routes are then aggregated and summarized as they move up the hierarchy towards the core of the internet. And as I mentioned a moment ago, security is a key characteristic, and it is of a significant concern when we talk about exterior routing. So protocols like BGP have been vulnerable in the past to route hijacking and other types of attacks. And so efforts have been made to enhance BGP security, such as leveraging things like a resource public key infrastructure for prefix validation to make sure that those exchanges are actually valid. Similar to spanning tree protocol and L2 switching, we also have convergence time when it comes to BGP. And so exterior routing protocols like BGP are designed for stability and reliability. And so they often have mechanisms to minimize the amount of route flapping and ensure smooth convergence when changes in routing occur. And as I talked about a moment ago, multi-homing. So for high availability and redundancy, BGP provides the support for multi-homing, and this allows organizations to connect to multiple ISPs for redundancy and load balancing. So many of your largest colos, when you go into them, or public cloud providers, they will be multi-homed, meaning they have multiple ways to get to the core of the internet in case one provider goes down. And that leads into global reachability. So the primary goal of BGP and other exterior routing protocols is to ensure global reachability. We want to make sure that everyone is connected on the internet. And so this allows data to traverse the internet and reach its intended destination, regardless of the number of ASs it must traverse. This next slide covers a little bit more about autonomous systems and specifically how the ASNs are assigned to external entities. Each region in the globe has an internet registry that is going to assign these external ASNs to different organizations and network providers. And this is going to make sure that we have unique ASNs across the internet so that we don't have duplicates and have competing routes being injected into the internet backbone. So when we think about BGP, you also have to think about BGP peers. So two different networks talking to one another and establishing a connection and exchanging routing information. And so when we think about that, there are three key things to remember. First, there's BGP peers, then there's BGP sessions, and then there's the BGP table itself. So a peer is exactly what it sounds like. It's going to be my neighbor on the network, whomever I am talking to next. More than likely, it's my upstream provider that I'll be peering my organization's local data center with that larger ISP or telco network that I'm provided service from. And then we have BGP sessions, and BGP sessions are essentially that joining of those two network entities to be able to exchange information and exchange routing. And then we have the routing tables or the BGP tables themselves. So this is going to be where I, as an organization, advertise up to my provider the networks that I'm publicly making accessible over the internet for them to establish a BGP session with, so that they know that I have those networks within my organization or within my AS. It's really these three components that form the foundation of the actual BGP peering between two different entities. So again, my peer, my session itself, meaning the information that I'm exchanging, and then the BGP table. So the routes that I have and the routes that my upstream provider is aware of. And one last thing to remember before we move on from this part, whenever you're troubleshooting a BGP issue, the first thing that you should be looking at is your BGP table to see if you have your sessions established and in a correct state. We're going to go over in just a few moments the different states that we can find ourselves when two peers are establishing a session with one another. So next, I want to talk about BGP's best path algorithm. And so BGP uses a complex decision-making progress called the best path algorithm to select the best route to reach a specific destination network. And the algorithm is going to take into account various attributes associated with each BGP route and assign a preference value to each route. Some of the key attributes considered by BGP best path algorithm include the AS path. So the path, again, is the route taken through different ASs. Then we have the next hop. The next hop is the IP address of the next hop router to reach the destination. Then we have local preference, which is a locally configured preference value. Then we have MED, or multi-exit discriminator, which is an attribute used to influence routing decisions between different ASs. We then have wait, which is a Cisco-specific attribute used to influence the selection process. Now, BGP selects the route with the highest preference value as the best path. And so if multiple routes have the same preference, other factors like AS path length and router ID may be considered. And once the best path is selected, it is added to the BGP forwarding information base, or FIB, to determine how to forward traffic destined for that network. So let's talk more about the BGP message types. And so there are various messages that are going to be used to exchange routing information and maintain the routing tables between BGP routers in different ASs. And so the first type of message that we have is an open message. And this is the first message that's going to be exchanged between BGP routers when they establish a BGP session. Now, it's going to include information about the sender's BGP capabilities, such as the version number, AS number, and optional parameters. And if both routers agree on the capabilities, they then proceed to establish the BGP session itself. The next type of message is an update message. And this is the most critical BGP message type because it carries routing updates, including information about reachable prefixes or network routes and the associated path attributes. And the path attributes help routers make routing decisions based on policies and path information. An update message can include several different pieces of information. The first piece that it can include is a withdrawn route. Now, it is just what it sounds like. It's a withdrawn route is now a route that's no longer valid and should be removed entirely from the routing table. The second piece of information that it can include is a path attribute. So now this could include information like the AS path, the origin, the next hop, and many more things. And these are going to be used to help the routers make routing decisions themselves. And finally, we have network layer reachability information, or NLRI. And this is going to include details about the reachable prefixes and their associated path attributes. Now, after the critical update message, we have a keep alive message. And keep alive messages are used to maintain the BGP session's liveliness. Now, they're typically going to be sent periodically, about every 60 seconds, between BGP peers to ensure that the connection is still active. If a router doesn't receive a keep alive message within a certain time frame, it may consider the BGP session is down and take appropriate action. Finally, we have the notification message. Now, the notification message is sent when a BGP router encounters an error condition or decides to terminate the BGP session. It informs the peer about the error and provides a reason for the session termination. Now, some common reasons for sending notification messages include BGP session resets, authentication failures, or other errors. Let's take a minute and talk about how BGP messages work. So first, we have the session establishment. And this is going to be that when that open message is sent between BGP peers so that they can then agree on the protocol version that they're going to be using and the capabilities of BGP between those two individual routers. Next, we have the route advertisement, and this is exactly what it sounds like. The two routers are going to advertise to one another the routes that they have available so that they can update their BGP tables. Next, we have the path attribute analysis when the BGP peers are going to figure out the best path for all of the routes that are advertised between the two routers. After the best path analysis is completed, that's when we're going to create the route selection, and we're going to decide what is the best path for each of the networks that are attached and being advertised between the different BGP routers. Finally, we have those keep alives and those notification messages that are going to be sent continuously, or the keep alives will be sent continuously between the BGP routers, and then the notification will be sent if there's an error condition, as we discussed a moment ago. And finally, we have those continuous update messages. And again, those update messages are the most critical BGP messages that will be sent between different BGP routers because they're going to include updates so that we know what new networks are now being advertised, what networks are being pulled, and so forth. And so this is going to be really critical as a message type between different BGP routers. So now we've discussed the different BGP message type. Now let's spend a few minutes talking about the different BGP neighbor states. So again, BGP neighbors are BGP routers that form relationships to exchange routing information between one another. And these relationships goes through a series of states from idle all the way to established in order to establish and maintain a functional BGP session. Now, the established state is the desired state where routing updates are exchanged, helping routers make routing decisions based on policies and path attributes. Now, as we go through the 6 states on the slide, let's start with the first state, which is the idle state. Now, this is going to be that initial state when no BGP session has actually been established. And in this state, the BGP router is waiting for the configured neighbor's router ID or IP address. So this could be you've configured the first router for BGP, but you haven't yet configured the second router for it to know about its new neighbor. And so one of them will be in that idle state. Next, we have the connect state. And this is when a BGP router receives information about a potential neighbor, i.e. either the router ID or an IP address, and it's transitioning to the connected state. In this state, the router is going to attempt to establish a TCP connection to the neighbor. Next, we have the active state. So if the TCP connection attempt fails in the connect state, the BGP router will enter this active state. In this state, the router repeatedly tries to establish the TCP connection to the neighbor. And so if you're having a problem where you see your BGP neighbors in this active state consistently, then you have some sort of TCP network issue between those two routers you need to look into. Next, we have the open sent state. So once a successful TCP connection is established, the BGP router enters this state, and the router sends an open message to the neighbor, which includes information about the router's BGP capabilities. Again, things like the version number. Once that's done, we have the open confirm state. So once we've sent that open message, the BGP router enters into this open confirm state where it's expecting to receive an open message from the neighbor that it's communicating with, acknowledging the capabilities that the two have. Finally, we have the established state. So when both routers have successfully exchanged open messages and they've agreed on the capabilities, now they're going to transition to this established state. And again, in this state, the BGP routers can now exchange routing updates using those update messages. They can exchange keep alive messages to be able to maintain the session between one another. And they'll also from time to time send out those notification messages in case of issues. And the neighbor relationship is fully operational in this state. So when you're troubleshooting a BGP issue, as I mentioned a moment ago, the first thing that you want to look at is that BGP table, because that BGP table will show you the state that those two BGP peers or BGP neighbors are in. And if you see anything other than established, then you're having an issue. Now, the other thing that I will mention is that the open sent and the open confirm state, those are usually very difficult and you'll rarely actually see them in the BGP table when you're looking for them. So typically you will see idle, you will see connected or active, and then you'll see established. And again, anything other than established means that you're having an issue between those two BGP peers or BGP neighbors. Moving on from the different BGP neighbor states, the next thing we need to discuss is route summarization. And so route summarization is used by network administrators to identify a set of contiguous IP prefixes that share a common network portion. And these prefixes are typically part of the same IP address subnet or address space. And so we're going to identify potential aggregations that we can create. The next thing we're going to do is create the summary route. So once we've identified those contiguous IP prefixes, we're going to create a summary route, also known as a super network or aggregate route. And this summary route is going to cover a broader range of IP addresses that encompass all of the individual prefixes in it. Next, we're going to actually start to advertise out that summary route. So instead of advertising all of these individual prefixes separately, routers are going to just advertise that one larger summary route. And this is typically a single shorter prefix that represents the aggregated address space of the individual prefixes. And this is going to allow us to optimize the routing table. So routers that receive a summary route can use it to make routing decisions. And then they store that summary route in their routing tables, which reduces the number of entries required to represent the same set of destinations. And this optimization is going to significantly reduce the size of the routing tables themselves, and it's also going to conserve memory and CPU resources on those physical routers. So when we are thinking about this route summarization that's going to take place, there are really 4 key benefits that we want to lock in on. The first is going to be that reduced routing table size, as I just mentioned a moment ago. This is going to also improve routing efficiency. By not having to advertise dozens and dozens of smaller segments, network segments, we can summarize those routes into a singular one. So this is going to improve our routing efficiency because it will reduce the amount of decisions that routers have to make from a vector path analysis perspective. In addition to that, when we summarize all of these routes together, this is also going to now reduce the convergence time that we talked about. So when updates happen and we're now suddenly advertising a new network segment or new network block externally, if it's part of this greater route summarization that we've created, then we're going to be able to reduce the convergence time because in most cases, the networks will already know about it. And finally, along those same lines, it's also going to reduce the amount of BGP update traffic that we are sending across the network between the different routing or BGP neighbors and their established sessions. So this concludes our BGP deep dive for Module 6 in my Networking Fundamentals course. I hope you're enjoying this content. Please make sure that you check out the playlist which I've created with all of the modules so that you can watch this series start to finish. If you're enjoying this content, specifically this Networking Fundamentals course which I've created, please make sure that you leave a comment below and let me know what you think. And also consider subscribing to my YouTube channel @VirtualElephant, and make sure you turn on those notifications so that you're notified when I release new videos. I'll see you next time.